Welcome to the ISSCC Circuit Insights, Frequency Behavior of Circuits. Let me introduce myself. My name is Nan Sun. I got a bachelor degree from Tsinghua University in 2006 and a PhD degree from Harvard in 2010. I worked with UT Austin for 10 years, and since 2020, I've been with Tsinghua University as a full professor. My research interests include data converters, analog front-ends, sensor interface circuits, analog circuit design automation, and emerging applications. So let's get started with a very simple circuit. So consider a resistive load RL driven by a signal source with a source impedance Rs. We can easily get the relationship between the output and the input. That is, V out equals V in times RL divided by the sum of Rs and RL. The source impedance and load impedance forms a voltage divider, and the output is a real-time response of the input with a fixed attenuation ratio. So the behavior of this circuit actually does not depend on frequency. The response is instantaneous. So now let's take a look at a situation when the load is a capacitor, which is also very common in circuit design. We know that the charge on the capacitor is the integration of current. This means the capacitor needs some time for charging and discharging. So we cannot get real-time response like we do in the last slide with the resistor. Intuitively, we can say that the output can track the input if the input change very slowly, because the capacitor has enough time to be charged and discharged to follow the input variations. This is exactly the concept of frequency behavior, which is actually our theme today. So the Laplace transform and the transfer functions are powerful tools for analyzing the frequency behavior of circuits. And the RC network, composed of source impedance and load impedance, forms a low-pass filter. We can get the transfer function to describe the frequency response of this circuit from input to output. And the frequency response can be separated into amplitude response and phase response. So like shown here, we can see that the first part, in red, is the amplitude response, and the blue one in the second part is the phase response. We can draw the magnitude plot and phase plot in this graph, which is called the Bode plot. The magnitude and the frequency are usually in decibels. At low frequency, the magnitude is about 1, which means the amplitude of the output signal is approximately the same as that of the input. This is consistent with our intuition that the output can track the slowly changed signal. As the signal frequency increases, the output amplitude drops. This is why we call it a low-pass filter. Only low-frequency signals can pass it, while high-frequency signals are blocked. The corner frequency, which is defined as the frequency when the magnitude response drops 3 dB below the low-frequency value, is 1 over RC. The phase response is also easy to understand. At low frequency, the output tracks the input, and thus there's no phase difference. At high frequency, the SRC part dominates and brings a 90-degree phase shift. So let's take a look at some examples. So here, the blue line is the input, and the orange line is the output. So with the low frequency input, when the frequency is much lower than the corner frequency, we can see that the output and the input, the amplitude-wise, is pretty much the same, and then there's slight phase delay for the output comparing to the input. When the input frequency approaches the corner frequency, so we can see that the amplitude gets smaller and the phase delay gets enlarged. As the input frequency increases further, so now its input frequency is much higher than the corner frequency, we can see that there is very clear amplitude decrease, and there's also a larger phase delay. We can see that the phase delay is approaching 90 degrees, and this is also what is predicted from the Laplace transform. Okay, so after taking a look at very simple low-pass filter, let's move to a more advanced circuit. So now if we want to amplify a signal, how could we do that? Well, I believe that all of you know that transistors can be used to build amplifiers. And here is a very simple common source amplifier driven by a signal source. We call it common source because the source of the transistor is tied to ground at fixed voltage. Given a proper DC biasing point, we can use this circuit to amplify the input signal. When doing small signal analysis, we can replace the transistor with this small signal model. For simplicity, here we use a very simple first order model, basically a voltage controlled current source, VCCS, to represent the small signal model of a transistor. I think you're quite familiar with this circuit, right? So the GM is the gain from the gate to source voltage VGS to the current, the drain current ID. It is determined by the operating point of the transistor. According to the long channel model, the transconductance GM is equal to ID divided by overdrive voltage VOV times 2. So replacing the transistor with the small signal model mentioned above, we can get a small signal circuit shown on the right-hand side. It is quite easy to calculate that the small signal gain from the input of the amplifier to the output is GM times RL. So now let's take a look at an example, and here we assume that transconductance GM is 4 millisiemens and the load RL is 1 kilo ohm. Then the small signal gain, according to our calculation, should be 4. So now let's bias the input and output node at 500 millivolt, and we introduce a small AC signal at the input, which is in blue, and the AC signal is of 1 millivolt amplitude and frequency of 10 megahertz. And the output signal, which is the orange line, is amplified but with a phase difference, 180-degree phase difference, and then its magnitude is get amplified by 4 times. And this matches pretty well with our expectation. Well, what if we increase the frequency, the input frequency, to 100 megahertz? And we can see clearly that now the output magnitude drops below 4. The gain is less than 4. And this is, well, the amplitude gain decrease as a function of input frequency increase. So we further increase the input frequency, for example, to 1 gigahertz. So now we need to zoom in to get a clear view. And the zoomed in view is shown here. And we can see that the amplitude it gets even smaller. And the output actually is even smaller than the input. So this is no longer an amplifier, but actually an attenuator. So what happened? Why? So actually you may discover that this is quite similar to the low pass effect that we talked about at the beginning of this talk. In fact, there are many capacitors in transistors, and that's why the output signal varies with different frequencies. So now let's take a look at the principle how a transistor works and where are the capacitors. So when the transistor works in the triode region, the source and drain node are connected via a conductive channel. In this situation, the gate and the channel forms a parallel plate capacitor across the gate oxide. The capacitance can be easily calculated using the parallel plate formula, and it's quite easy to show that the total channel capacitance is given by W times L times Cox, and Cox is the unit capacitance, and Cox is given by the epsilon ox divided by the Tox, which is the thickness of the oxide. And here in the triode region, we can approximately assume that the drain and the source are symmetric. And in this condition, the capacitance between the gate and the channel CGC can be equally distributed on CGS and CGD, and therefore we can have the CGS equals CGD equals the total channel capacitance divided by 2, which is CGC divided by 2. So when the transistor works in the active region, the channel is pinched off. The drain voltage has little control over the channel charge. So now the channel charge is almost completely controlled by the gate to source voltage, VGS. However, because the charge in the channel is no longer uniformly distributed, as shown here, it's more like a triangular shape, the capacitance gets modified. And the DTO calculation can show that now the capacitance between the gate and the source is 2/3 of the total kind of like parallel plate channel capacitance. And it's given by 2/3 times W times L times the unit capacitance Cox. And CGD, as we mentioned, is almost zero because the drain has little control over the channel charge. So when the transistor is off, there's no conductive channel, and the gate sees a capacitor as a substrate, which is equivalent to the series combination of gate oxide capacitor and the depletion capacitance. Therefore, we can summarize the MOS transistor intrinsic capacitance in this table, and we can see that depending on different region it operates, the capacitance CGS, CGD, and CGB are different. And for analog circuit, we're usually interested in the active region, and in the active region, we can see that the CGS is the dominant part, the CGD is almost zero, and the CGB is also zero. And here, the CGB is the gate-to-bulk capacitance. Okay, so now we revisit the common source amplifier that we showed earlier, and we know that the source impedance is 10 kilo ohm, and the gate source capacitance is 24 femtofarad. So we can calculate the amplifier bandwidth, 3 dB bandwidth, is 663 megahertz. However, the simulated frequency response show that the amplifier 3 dB bandwidth is actually 206 megahertz. It's not 663 megahertz. There's a large error in the estimated bandwidth. So this means that our simple bandwidth expression is actually inaccurate. So why? Well, the reason is that we have neglected the extrinsic capacitance that also affects the frequency response of our amplifier in a significant way. So this example shows that we need a more accurate capacitance model for our transistors. And here, when I talk about extrinsic versus intrinsic capacitance, what I mean is that intrinsic capacitance are the capacitance that are fundamental to the MOSFET operation, which is the channel kind of charge behavior. For extrinsic capacitance, they're not fundamental to the MOSFET operation. They're there because of idealities. Well, let's take a look at a cross-section view of a transistor. We can identify some extrinsic capacitances here, including the overlap capacitance between the gate to source and gate to drain, as well as the junction capacitances from the source to bulk and the drain to bulk. And for simplicity purpose, we ignore the junction capacitance and let's focus on the overlap capacitance, which are also usually the dominant extrinsic capacitances. So the overlap capacitance include two components. One is the exact overlap between the gate and the source and the gate to the drain. And this capacitance can be modeled as a parallel plate capacitor and can be easily calculated as Cox times W times L overlap. The other component results from the fringing field, which is kind of the more like a three-dimensional fringe capacitors. And these two components, they're proportional to the width of the transistor. And we can use a simple model to calculate them, which is the C overlap is equal to C overlap prime, which is the unit overlap capacitance times the width of the channel. And for 0.18 technology, we can have that for PMOS and NMOS, the unit overlap capacitance are about 0.8 or 0.7 femtofarad per millimeter. So now, including the extrinsic capacitances, we can modify the table into the one shown here. Again, we're mostly interested in active region for analog circuits, and here we can see that the CGS is modified to 2/3 of W times CL, L times Cox, plus an overlap capacitance C overlap, and for CGD it was 0. Now it needs to be modified to C overlap. Okay, so now let's include CGD into our small signal model, and we can get the circuit shown in this slide, shown on the right-hand side. So how can we calculate the transfer function and figure out the bandwidth then? Well, we can cut the circuit and calculate equivalent admittance seen into the right-hand side of this circuit, basically looking to the right-hand side of CGD. We can then get expression shown above. The admittance is SCGD amplified by 1 minus AV of S. So here AV of S has one pole and one zero. So if we assume that the poles and zeros in AV of S occurs at very high frequencies, much higher than the bandwidth of the amplifier that we were estimating, then it is okay to replace AV of S with this DC value, and this is what we call the Miller approximation. Well, sure, we have to check the validation of the approximation later. We cannot just take it for granted, but we'll show that this approximation is actually valid. So if you replace AV of S with its DC gain value, which is GM times RL, then the admittance is now 1 plus GM times RL times SCGD. And this is actually the same as the capacitor to ground with the value of 1 plus a GM RL times CGD. So this is to say that the equivalent circuit of the right-hand side is actually an amplified capacitance. So this way, the input network is actually can be much simpler. We can easily get the expression of the bandwidth, and we can show that how accurate we can actually match spikes. So using the known data, we can recalculate that the 3D bandwidth now is 200 megahertz using the CGS of 26 femtofarad and CDD of 11 femtofarad that we can get from simulation or calculation. And then we can see that this actually matches pretty well with our simulation result, which is 206 megahertz. And this shows that the Miller approximation is actually quite accurate, and also it shows that by including the extrinsic capacitance model, now we can estimate bandwidth accurately. So now let's take a look at the assumption, well, whether the Miller approximation is valid. We assumed that the pole and zeros of AV of S occur at very high frequencies. We can actually calculate the magnitude of this, the pole and zero locations, and we can see that they're actually at 14 gigahertz and 58 gigahertz, which are indeed much higher than the amplifier bandwidth. So our assumption indeed holds true, and that's actually why that our estimated bandwidth of 200 megahertz matches pretty well with the spike simulation result. But what if we now add some load capacitance at the output of amplifier? And this is also quite common because our amplifier has to drive some capacitive load. Well, we have to rederive AV of S, including the effect of CL. And we can use KCL and KVL to derive that. We can show that expression is given here. The zero location is unchanged and it's still very high frequency, but the pole location of AV of S gets changed. It is lowered with large load capacitance. So if load capacitance is 10 picofarad, we can show that the pole of AV of S is at 16 megahertz, which is much lower than 200 megahertz. And this means that the Miller approximation is no longer valid. So what's going on with this modified circuit with a very large load capacitance? Well, the CDD is amplified only at low frequencies before CL destroys the gain from BGS to VL, or basically the gain of AV of S. The pole caused by CDD no longer sets the 3 dB bandwidth of the amplifier. Intuitively, the bandwidth must now be set by CL. So after all, it destroys the gain from BGS to V out, which implies that the gain from V in to V out must also roll off. So with a very large CL, we can expect that the approximate bandwidth of the circuit should be 1 over 2 pi times RLCL. But how about other cases in other circuits that don't have a straightforward Miller approximation? Fortunately, there is a more general method that allows us to estimate the bandwidth of an arbitrary circuit without going through the pain of deriving the complete S-domain transfer function. It is called the zero-value time constant analysis, or ZVTC analysis. And here is how it works. So first, remove all but one capacitor and short independent voltage sources and remove independent current sources. Then we calculate resistance seen by the capacitor and compute a time constant which is equal to RC. And then we repeat for all capacitors in the circuit. And the last, we sum all time constants and calculate the bandwidth estimate the omega 3 dB, which is 1 over the summation of all the time constant that we have calculated. So let's take a look at a circuit example and show you how we use the ZBTC analysis to calculate the bandwidth. So first, remove all capacitors except C1, and we can get the circuit shown below. And it's very easy to show that the resistance seen across C1 is simply the source impedance, Rs. And we can get the first time constant, tau1, which is equal to Rs times C1. The next one is C2. So we basically remove all other capacitors and we're looking into C2 and calculate the resistance. And the resistance calculation is more complicated, and after some efforts, we can get the second time constant, and it's equal to Rs times plus RL plus Gn times RL Rs, and then multiply by C2. And the third step is for C3, and it's pretty much the same as C1, and we calculate that the resistance looking into C3 is basically RL, and we calculate tau3 is given by RL times C3. So using the numbers from our design example, we can get that the 3D bandwidth using the DVTC technique is 194 megahertz. And this actually also matches pretty well with our SPICE simulation result. And as you can see here, what we do is that basically we calculate the time constant tau1, tau2, and tau3, and we sum them all up. And the estimated bandwidth is simply the 1 over 2 pi and then 1 over the total time constants. An expression is shown in the first line, which is a complete equation. So now let's include the effect of CL, and we make a very large CL of 10 picofarad. So here we can derive tau1, tau2, and tau3. And for tau1 and tau2, there's no change. But for tau3, now it's much bigger. It's now 1 kilo ohm times 10 picofarad, which is 10,000 picoseconds. And with this, we can show that basically the summation of all the time constants is dominated by tau3. And from here, we can calculate 3D bandwidth is 15 megahertz. So here we can see that the ZBTC technique is actually a powerful method. It includes Miller effect and also the loading effect. And it provides us the insights that which time constant is the dominant one, which capacitor is the dominant one. And here we can clearly see that the C3 is the dominant frequency limiting factor. So how ZBTC analysis works? Well, we can explain it in two ways, both intuitive way and also the mathematical way. So from intuition, each time constant relates to the bandwidth that we can get if no other capacitors were present and reflects only the local bandwidth bottleneck. So for simplicity, the ZBTC method linearly combines the local bottlenecks to estimate the bandwidth of the overall circuit. Mathematically speaking, the ZBTC method is based on some approximation of the transfer function. So suppose that there exists a dominant pole at a relatively low frequency than all other poles, then we can ignore all higher order terms in the denominator and calculate the total estimated bandwidth, and it's given simply by the summation of all the time constants from tau1 to tau n, and then 1 over that, right? So this process can show that the ZBTC analysis is okay, unless they're undamped complex poles or several limiting poles with similar magnitudes. So now let's make a summary. So in this talk, we looked at frequency behavior of circuits. For resistors, its behavior does not depend on frequency. But for capacitors, its impedance varies with frequency. And for MOSFETs, we looked at both intrinsic and extrinsic capacitances. And in this talk, we have also explained two techniques to analyze the frequency response of circuits. One is a simpler one, the Miller approximation, and the other one is more general, and it's the zero value time constant analysis. At last, I'd like to acknowledge Mingyang Gu from Tsinghua University. He's my teaching assistant and helped me greatly in preparing this lecture. I'd like to also thank Professor Boris Merman from Stanford University for sharing his lecture notes. So thank you very much for listening to my talk, and I look forward to meeting you all after COVID ends.